Meaning overall, the area is equal to pi times 10 squared is equal to 300. Or you can also say 200, I don't care. Freaking Gucci. A huge thanks to Brian for sponsoring this video. Good morning, fellow mathematicians. Welcome back to another video. A very nice subscriber of mine provided me with the other MIT 1869 exams. Today we are going to do geometry. Once again, improvised stuff. I hope I can do everything. And after that, there's going to come arithmetic. And speaking of arithmetic, new arithmetic merges out, also engineering clock. And do you know what the best thing is? Over the course of the whole Independence Day weekend, you're going to get 10% off everything at my Teespring shop. This merge, the new arithmetic and snack merge. The engineering clock doesn't matter by using the code FORTH at checkout. So if you don't have one already, get yourself one. It's a pretty good deal. Now we are going to dive right in. Today we are going to talk about geometry, and this consists of basically elementary geometry here. I have done an introduction to those exams, to those entrance exams last time around. So if you don't know what I'm talking about here today, take a look at the Hard Exams Gone Wrong playlist and you are going to find all the information there about the algebra one. And this is basically part 2 out of 4 of this entrance exam for the MIT guys from 1869. So when we take a look at this exam, you might notice that we have 7 questions here, and they range from 3-sided polygons, so like triangles, up until some similar polygons. Really doesn't matter what the dimensions are. What you also need to know are like the radius formulas or the area formulas. So it's quite interesting what they want from you here, and they basically also want you to use Papa Pythagoras, so like all the really important school theorems that you are ever going to learn, like the height formulas and whatsoever. It looks quite interesting to me, and I think it should be doable in quite a short amount of time. After this tiny little introduction, I'm going to give the commando now to Papa Flammy over there. Are you ready, Papa Flammy?
What's going on, smart people?
Alright, great. And he's going to solve some stuff at the chalkboard, and I hope he's going to be able to do all the exercises here. And I'm going to see you soon with a few last words. Konnichiwa, minasan, Flammy here. We are going to solve this right here, improvised, like just with the algebra part. And I'm pretty certain that I can solve everything here yet again. I'm not certain how long it's going to take though. For one theorem I have seen kind of appear in the first exercise. While reading through it, I have actually asked in my Discord server what it's called in English. In German it's called the Wechselwinkelsatz. So yeah, there goes. We are going to make use of that, I suppose. And as far as proving stuff in the 1869s is concerned, I'm pretty certain that they weren't too rigorous back then. And I'm going to do the proofs kind of in an elementary geometry style way. I think this is how they did it back then. Meaning we are going to cut stuff up and glue it back together. So we are going to go about this kind of heuristically. I'm going to give you basically the sketches of the proofs, and if I'm able to do them, and then you can basically stitch everything nicely together and rigorously using the theorems I have in my head. We are going to dive right in. The first one proved that the sum of the 3 angles of a plane triangle equals 2 right angles, meaning pi. So this is like a standard exercise. I also showcase using paper in my classes when talking about the interior angles of a triangle. What you can do is you take a parallel line to one of the sides here and put it at the opposite edge. Meaning, for example, we take a parallel line parallel to this one right here and put it on top. Now, what we are going to do, I have colored chalk here actually, because this makes it a bit easier to visualize. I'm going to cut a piece of paper basically up at this point, and I'm going to put this triangle into here, okay? We are going to take this triangle and put it here. Same spiel here, taking this triangle, and we are going to put it here. Meaning overall, if this was our angle alpha, and this was our angle beta and gamma and so on, by cutting it up and putting it up here, this is gamma yet again, and this up here is our beta yet again. And I have to take for granted that a straight line has pi radians basically, and yeah, has an angle of pi. This basically concludes it. Alpha plus gamma plus beta is going to add up to 180 degrees. And you can formalize this a bit more using a theorem I have talked about a few minutes ago, namely the alternate interior angles theorem. So if we have two parallel lines, and this is just a special case of this, and we put a line through it, okay, straight line, then for example, if we have our angle beta here, then this angle on the opposite side basically of the line is going to be the same angle yet again, beta. And this is what we basically did here. Extend this line, then we have this line going through it, and then we have beta and beta, and you can do the same spiel for gamma, and then you are done. This is basically how I would approach this exercise. Next exercise had something to do with a parallelogram, I think. Prove that the diagonal of a parallelogram divides it into two equal triangles. This should be actually kind of easy. Let me think for a second. Okay, I mean, a parallelogram has a nice property that the opposite sides are always parallel in some way, and due to them being parallel, they also have the same side lengths, the opposite side. So this is B, and this is A, and this is A. And also as a consequence of the parallelogram, it's a really nice geometric form. We have that in the opposite corners, we have the same angles, alpha, alpha, and beta, beta. Now, we have to put a diagonal through two corners. I'm going to go for beta, beta, just because it's easier to see. Meaning, what we are doing now is we are going to put a line through here. Meaning, we are going to split up beta. I'm going to call this angle, I don't know, gamma yet again, and this right here, delta. Meaning, I don't even know if I need this, delta plus gamma is equal to beta in this case. And now, cool thing is, alternate interior angles yet again. If we extend this line, for example, those are going to be parallel yet again by the properties of a parallelogram. Then we have that the alternate interior angles tell us that this right here is yet again gamma, and this right here is going to be delta, meaning up here we have beta yet again. Meaning, since we have alpha in the corners here and alpha here, we have that those two are actually congruent, those triangles, because the interior angles are all the same on those triangles. Also, this line segment is B, this is A, this diagonal, I'm going to call it D, okay, is also the same as the one in here. This is also D, this is A, and this is B. All three side lengths of those are equal. The interior angles are equal, making them congruent. So turn this around, put them on top, and they are going to be deckungsgleich, all right? As you would say in German. And I believe this should conclude, was this even the exercise? Divides it into two equal triangles. Yeah, they are congruent, and this basically does the job. Prove that the area of a trapezoid is equal to the half sum of its parallel bases multiplied by its altitude. Let me get this straight really quick. The area of a trapezoid, AT, is equal to half the sum of its parallel bases. Let me draw one really quick. So I'm going to make this a bit exaggerated, like this. So this is A, B, C, and D, meaning the sum of its parallel bases, A and C. So A plus C multiplied by its altitude, and this whole thing half, so over 2. I think we are, this is something I always show my students, gluing up, cutting stuff, gluing it back together. This is what I do all the time. So we are going to take our trapezoid that we have here. This is just standard stuff I show my students all the time. Okay, I'm going to use the exaggerated one yet again. And now we are going to copy this one up, meaning we are going to take 2 times the area of the trapezoid. We are going to copy this one, we are going to rotate it and put this trapezoid here yet again. Alright, I hope you can see where this comes from. Now we have 2 times the area of the trapezoid, and this basically works for all the really easy geometric figures, for triangle areas, etc., rectangle areas, blah blah blah. Okay, and now, not for rectangle areas, just because we are going to bring it back to a rectangle basically. Now, we are going to, where's my chalk? We are going to cut it up at this part, okay? Now we are going to take this triangle and put it here. Okay, now what we have is, our C is going to be preserved here. Our A is what we put here, A and C, okay? If we take this away, we are going to be left with a rectangle. And what we had here is basically the height they are asking. Meaning, A plus C is the base times the height is going to be A plus C times the height is going to be 2 times the area of our trapezoid. Now we are going to divide both sides by 2 because it's not equal to 0. And thus we are done. I love those exercises. They are really cool and you can demonstrate it really nicely using paper at a chalkboard. So if you are a teacher out there or someone striving to become a teacher, use this elementary geometry method. It really works wonders even for students. They really understand it way better using this method. Prove that the side of a regular hexagon inscribed in a circle is equal to its radius. Whew, that is interesting. Okay, so we have a circle and we are going to inscribe a hexagon in it. Hexagon is one more than a pentagon, meaning we are going to have something like, okay, this. Okay. And now what we have to do is we have to prove that the side of a regular hexagon inscribed in a circle is equal to its radius. Meaning if this right here is the radius, then we need to show that those side lengths are also the radii or the radius. It's a regular one, meaning all the side lengths are equal. That's actually quite easy. In a hexagon, how many degrees do we have in there? So we have 180 degrees and then 4 times 180 is going to give us 720 degrees interior angles inside a hexagon, 720 degrees. Meaning in each corner here we are going to have, this has 6, so 120 divided by 6 is going to be 120 degrees in each and every corner. If we partition this thing up like this, okay, I hope you see where I'm going at. Since this is a regular one, side lengths are equal, we are going to divide those interior angles up in half, meaning 60 degrees. So each of those in here is actually 60 degrees. This is 60, this is 60. Since it's a triangle, we have 180 interior angles. This is also 60. Making this an equilateral triangle. Since this is the radius, so all side lengths in an equilateral triangle are equal since the angles are equal. So this is the radius r, this is the radius r, making our outer side equal to the radius r. I don't need this implication arrow. And this should basically conclude it. Yeah, you are just going to play around with the interior angles. What you basically need to prove only is that if you cut those interior angles up one by one, it's going to result in 60 degrees. But this shouldn't be too hard to prove because we are going to have a parallelogram here. This is the radius, this is the radius. Those are going to be parallel, meaning those are also parallel. They have the same side lengths, meaning we are going to divide this thing up into, this is crazy cool. So like this with the parallelogram is even embedded in here. I don't know if you need it, but this is cool. And then we are going to divide this up into 2 equal triangles where this is 60 degrees, this is 60, etc. This is crazy cool. This is really nice. I should look more into this, but yeah, this is like my improvised proof. Cool. So this was a lot of fun. Next up, the radius of a circle equals 10. Find its area. Are you shitting me? So area of a circle is pi r squared, meaning overall the area is equal to pi times 10 squared is equal to 300. 300, you get it, pi is equal to 3, or you can also say 200, I don't care. Freaking Gucci. Okay, this was easy. No, it's more like 314, I'm terribly sorry. Now, number 6, the perpendicular drop from the vertex, oh this is a long take, from the vertex of a right angle upon the hypotenuse divides it into 2 segments of 9 and 16 feet respectively. Okay, we have a right triangle in some way. We are going to drop a height, which is perpendicular to our base, and it's going to divide it up into 16 feet and 9 feet. And what we need to find out is the length of the perpendicular, okay, so this length and the two legs of the triangle. Okay, this is our height. Then we have the Höhensatz. I can't remember for shit what it's called in English. H squared is equal to, so if this is our P and this is our Q, if our hypotenuse gets cut up by some kind of height, then we are going to get 16 times 9. Meaning our height, since it's defined positive in the Euclidean space, is going to be the square root of 16 times 9. I think. Should be. Okay, now that we have that, you can easily get the square root of this thing, doesn't matter. But I think we can leave it in square roots just because we are going to use Pythagoras now, Papa Pythagoras. So if this right here is our B and this is our, if this right here is our A and this is our B, we are going to have that A squared is nothing but, or A is nothing but the positive square root of H squared, so 16 times 9 plus 16. Okay, this is going to give us a square root of 16 as a common factor is 4 times the square root of 9 plus 1 is going to give us 10. That's a weird answer, but I suppose it's right. 4 times square root of 10. Yeah, seems right to me. Okay, yeah, I thought they would get nicer values out, but let us... Oh no, I forgot this... Oh, yeah, what did I do? I forgot the square on the 16. Yeah, I was confused by this. 16 squared. Then we have, 16 as a common factor. 4 times the square root of 9 plus 16 is equal to, that's 25, so makes 20 overall. I was already thinking, why should they have such weird values? Because I think in those tests you need to give decimal values, and that would be just kind of weird. So like with decimal places and giving this for square root. I mean, it's a nice exercise, but I don't think that considering the amount of time they had only on their hands to solve like 4 parts, I don't think that they should calculate square roots up to decimal places. And now for B, we are going to have the same thing just with a 9 here instead of a 16. So 16 times 9 plus 9 squared is going to be square root of 9. So this makes 3 times square root of 25 yet again gives us 15 overall. And I think this should do it. And now we only have one exercise left, namely define similar polygons to what are the areas proportional. I'm going to do this on a fresh blackboard. So for the last question, I have interpreted like this. So we are going to have some similar polygons given, meaning they are just like 2 polygons, like really doesn't matter. Let's take a rectangle with side lengths 2 and 3, and we are going to scale it up. All the angles in there are going to be preserved. All we do is scale the shit up to like 4 and 6. We are going to double the side lengths, for example. There's a scaling factor. To what are the areas proportional? Since from the dimensions from a physical point of view, they are proportional to the scaling factor squared. Meaning if this is just my interpretation here, and it should be right, I think. So our area 1 that we have here, for example, for the first one, is going to be 6, 2 times 3. Meaning that's our origin area. And now if we scale this thing up, area 2, we have doubled the side lengths. This is going to give us 24. 4 times 6 is 24. So this is 4 times 6. And this is our origin area. This is area 1. So this is 4 times area 1. And 4 is nothing but 2 squared times area 1. Meaning we have doubled the side lengths, 2. And we are going to take it squared because from the dimensions speaking, we have meters squared, for example, as the units. So just some dimension analysis here. And I think the same spiel should work with all the other polygons that you can possibly think of. Let us take a look at a triangle, for example, a right one. It's just a special case, but it should work for all polygons, I suppose. Let's say side lengths 2 and 1, meaning our height by the Höhensatz is nothing but square root of 2. This is what we had before, meaning our area 1 of the triangle is the base, which is 2 plus 1, is 3, times the height over 2. This is our area 1. If we now were to double up the side lengths here, we are going to have the height yet again. This is going to grow 2. This is 4 and this is 2, meaning the height overall is square root of 8. Square root of 8. Square root of 8. Let's trace it back to the square root of 2. Is going to be square root of 4 times 2, square root of 4 is 2, so this is 2 times square root of 2, meaning our area 2 is thus nothing but the base, so 4 plus 2 is going to be 6, times the height, 2 times square root of 2, over 2. Now 6 is nothing but 3 times 2, and this means we have our area 1 preserved, 3 times square root of 2 over 2, and 2 times 2 is 2 squared, so 2 squared times area 1. Meaning if we were to take the ratio of those, a1 over a2 is going to give us overall for each and every polygon. If we have a certain scale factor, then this is area 1 over the scale factor squared times area 1. This is going to cancel out, and what is left is 1 over s squared, and thus the proportions is 1 to the scaling factor squared, if you get where I'm going at. And I hope this is what the exercise wanted from me, and I'm going to give everything back to Papa Flammy, and I hope you did enjoy this improvised session, huh? Alright, I hope Papa Flammy did solve everything correctly there at the chuck, but otherwise it would be kind of embarrassing. On a serious note though, I can see why people considered those entrance exams, be it geometry, algebra, arithmetic, to be hard back in the days. Some subscribers told me that in the 1800s you got out of school with like 9th grade. And to be honest, I don't think that I ever covered in my school life, for example, hexagons being inscribed in a circle. I don't think that I ever covered this. And people had to know about this stuff up until 9th grade. They had to know about a lot of things here actually. If you take a look at this geometry exam, they had to know about a lot of polygons, triangles, right triangles, parallelograms, hexagons, also circles. They had to know about a lot of formulas and identities like the height formulas, alternating inscribed angles and area formulas. They had to know how to construct areas from other polygons. That's a lot of stuff you have to remember up until 9th grade, and I give kudos to those people. And I can see now why people consider this to be hard, because it's really a lot of stuff for a young person to remember. Apart from all the algebra and arithmetic stuff, they also needed to remember in order for them to pass those exams. So kind of a feat, to be honest. I had a lot of fun with this. I mean, I have studied mathematics in a way, and for me it's kind of easy to solve through those exercises. I can also only say that this was easy after I checked the video and hope that I got everything correct. But yeah, I hope you agree with me that for like 15-year-old people this was pretty hard. To be honest, I can see why it was considered hard. And if you also enjoy geometry in a way, or other types of mathematics, competitive problems, or like stuff that is going to prepare you for your STEM career, then I encourage you to try out Brilliant today. I hope you did enjoy part 2 of the 1869 MIT exam as much as I did. Even though the geometry being covered here is elementary in a way, I think that the exercises are interesting and playful nonetheless. If you also find joy in exploring geometry intuitively and interactively, then Brilliant could be the perfect fit for you. Brilliant is an online learning platform and app which focuses on active learning and problem solving. Brilliant can help you achieving your STEM goals by working through their over 60 interactive courses in maths, computer sciences and all sorts of scientific disciplines, including geometry obviously. You would have definitely been greatly prepared for the MIT exam by using Brilliant. A huge variety of geometry-oriented content to work around with can be found in their precious geometry collection, covering the fundamentals, fractals, all the way over to 3D geometry. So basically everything we have seen today will be covered one way or another on Brilliant. So go over there and check it out, it's really great. So if this feels like it's something for you, make sure to check out the link at the top of the description. With it, you are going to get free access to a portion of Brilliant to try it out on your own. And the first 100 people to actually make use of the link, they get 20% off an annual premium subscription, so try it out and support the channel this way. I thank you guys for watching. If you did enjoy this video, please like, subscribe, recommend channel fake. Don't forget, use the code FORTH at checkout at my Teespring shop to get a discount, 10% off everything in there. New snack merch, Arithmetic merch, and like the engineering clock. And other than that, I thank you guys for watching and I wish you guys a flammable day. Ciao.